All right, next up we have Team 6. My pleasure to introduce Team Lavara.
Hi everyone, today we're excited to present Lavara. When you've sat for an extended period of time, whether on long flights, car rides, maybe through rounds of presentations, you might relate to this sequence of events. In able-bodied individuals, we sit for extended amounts of time, and the pressure of sitting prevents blood flow to our skin. We experience this as discomfort, and it's what alerts us to move and restore blood flow. There are 302,000 paraplegic patients in the United States that are constantly sitting in wheelchairs, and like us, the pressure of sitting prevents blood flow to their skin. But these patients don't experience discomfort because they lack sensation in their lower limbs and remain sitting. Pressure ulcers are areas of blood flow or areas of skin damage caused by this lack of blood flow. At stage 1, local skin temperature rises. At stage 1, local skin temperature rises with inflammation and tissue hypoxia, but often goes undetected, leading to persistent redness and tissue breakdown, open wound formation, and severe secondary complications. Of the 302,000 wheelchair-bound paraplegic patients at risk, pressure injuries are or will be a reality for 85% of them, contributing to $26.8 billion in annual costs for hospitals. Currently, clinicians address this by teaching pressure relief strategies. Patients are taught to either lift up out of manual wheelchairs or tilt back in their mechanical power chairs at standardized 30-minute time intervals. Skin checks are the secondary line of defense, but clinician judgment is subjective and varies heavily by the clinical training or the skin tone of the patient. And compliance is uncertain. We have no way to track the timing of these strategies or to confirm that they're effectively restoring blood flow. In talking with clinicians, we revealed a need for individual alerts attuned to the patient's unique risk, grounded in physiological data that can detect this initial rise in local skin temperature, and with real-time monitoring to confirm these strategies are performed effectively and when necessary. We've also identified comfort, function, price, and ease of use as the most important qualities to integrate in our solution. And Lavara has addressed all of this with a low-cost disposable patch that alerts paraplegic patients of elevated pressure sore risk with real-time monitoring of skin temperature data.
We chose temperature as our metric because an increase in temperature is linked to an increase in inflammation, which is an early indicator of skin damage and pressure ulcer formation. We will be assessing temperature spatially instead of over time to mitigate the risk that the environment will have on our skin temperature readings. For example, the difference between being indoors versus outdoors today. This is backed up by the data, which says that across a symmetrical axis, healthy skin will have approximately the same skin temperature, but there will be a 2 to 3 degrees Celsius difference if one area is at risk for pressure ulcers. Our current competition includes a pressure sensing mat called the Sensoria mat, which is not individualized, low cost, or disposable, Podometrics, which is not low cost, continuous, nor does it give an immediate alert, and skin thermometers like SteadyTemp that are not optimized for pressure ulcers and do not give an immediate alert to at-risk patients, while Lavara does all 5. First, it's disposable because it'll be on the lower back, where it will be exposed to a lot of sweat and incontinence, so for ease of use, it can be changed every 1 to 3 days. And since it's disposable, it must be low cost, which we'll do by having all of our complicated, expensive electronics in a separate relay center that can be attached and detached with each new patch. Each patch has 62 thermistors that will be detecting temperature, making our design individualized, and they will be doing so continuously and giving an immediate alert when the patient is determined to be at risk. So for the user workflow, first the patient will put the patch on their lower back, which is where a majority of pressure ulcers occur in paraplegic patients. Next, they will connect their phone to the relay center, which will start sending data via Bluetooth. When an area has been detected to be a higher temperature than its symmetrical counterpart, an alert will be given that will prompt the patient to either lift up or tilt back in the pressure relief position, depending on the type of wheelchair they have.
Lavara is made up of 3 main components. We'll start with the flexible PCB patch. This patch contains all of our thermistors with an improved 1% tolerance for temperature sensing accuracy. The small size of these thermistors mean that they do not protrude from the patch, allowing patient comfort. The thermistors are connected to our relay center through an FPC connector. Disposing of the patch is as easy as disconnecting the cable and reconnecting a new patch. An outer wound dressing covers this flexible PCB for patient comfort and electronic safety. This outer patch is made of multiple layers, each with a specific use intended. The outermost layer is waterproof for safety, followed by a foam backing for patient comfort, and then the flexible PCB sits with a PDMS layer that includes holes for the thermistors that also provides electronic safety. Next, a moisture wicking layer provides a layer that will remove sweat and any moisture, which is also a risk factor for pressure ulcer development. And finally, a thin adhesive adheres the whole patch to the patient's skin. The second component is the relay center. This relay center contains 8 multiplexers, which receive inputs from all of our thermistors. The outputs from the multiplexers are then sent to the operational amplifiers, which finally send their signal to the microcontroller. The microcontroller uses Bluetooth Low Energy to interface with our final component, the user interface. Our user interface prompts the user to connect through Bluetooth and is compatible with mobile phone and computers, allowing Lavara to be accessible to as many patients as possible. Additionally, users are able to view trends and they can send their data to trusted caregivers or physicians to better their care. Lavara has come a long way from its conception. Let's walk through our design goals from proof of concept to present. Starting with our hardware design goals, our proof of concept used 3 thermistors and 1 multiplexer. Our minimum viable product then used 20 thermistors and 4 multiplexers, and our final iteration included 62 thermistors with 8 multiplexers. For our software design goals, we began with an Arduino, and for both our minimum viable product and final, we used an ESP32. For the physical appearance, we began with a breadboard and inflexible PVC wires, and changed these to flexible silicone wires for comfort, and we added an enclosure for the relay center as well as some parts of the wound dressing. Finally, we have 2 custom PCBs, one for the relay center and a flexible PCB with the full wound dressing layers included. And for our user interface, we began with nothing, then had a Wi-Fi integrated web page, and finally have an app that's compatible with mobile phone and computer that's Bluetooth integrated.
So now that our design goals have been met, we sought to test Lavara for efficacy. We started this by testing the thermistor response just in the Flex PCB and then retesting after we incorporated the wound dressing layers. We did this by testing only one side of the patch to model that temperature asymmetry. Based on the PCB testing, we can conclude that our thermistors successfully detect temperature within 2 degrees Celsius. This is one representative trial in which all of the thermistors on each side were averaged for comparison. And you can see that Lavara is able to rapidly detect temperature difference when heat is applied and notify the user of increased pressure ulcer risk. Not only are our thermistors accurate, but they're sensitive, with the max standard deviation only being less than 1 degree Celsius. And when averaged across multiple trials, Lavara is able to consistently detect this temperature difference within 2 degrees Celsius. After integrating the patch, we were able to maintain that sensitivity to temperature detection within the 2 degrees Celsius. And again, when averaging across multiple trials, Lavara maintained the consistent temperature detection. We did notice that when adding the wound dressing layers, it did slow the response time between the heating up and cooling down. However, this response time is still well below the time at which it takes for a pressure ulcer to form. So based on the data we've collected, we've identified some key challenges that we would like to improve. The first being the wiring from the relay center to the patch. We'd like to improve this by incorporating a Bluetooth connection to allow for more flexibility for the user. The second is we'd like to decrease that response time within our patch. So we'd be looking to refine our patch materials, which would hopefully allow for quicker heat transfer without an excess buildup within the patch. We also need to look at battery life to make sure that our patch is able to sustain this power for the entire 3-day duration that we want. So we'll be looking at improving our power bank for longer lasting operating time. Looking ahead, we'll be integrating the design alterations discussed. We'll be applying for patents and the relevant regulations. We'll continue in-lab testing and integrate clinical testing for efficacy and safety. And eventually we'll want to look into how this technology could be applied to new skin areas that are also prone to pressure ulcers, such as the back or the back of the legs. At Lavara, our mission is to restore awareness where it's been lost. Our patient-centered design can ultimately help make prevention possible rather than treatment necessary. We'd like to thank our mentors and our professors for their help and guidance. And thank you. We'll take any questions now.
Hi, nice job. How thick is the attachment up at the very, very top?
The connector?
Yeah, how thick is that?
So the entire patch is about 6 millimeter or 0.6 millimeters. So the entire patch is less than a quarter of an inch. The actual FPC connector is even smaller than that. It's a fraction of that entire patch.
Okay, and then I may have missed this. Is this just to alarm, or is it making some type of is the patch doing something as well, or is it just to alarm?
It's just to alert the patient
Okay.
based on the temperature sensing that it reads. Yeah.
Okay, great. Thank you. Nice job.
Great job. One question I had for you guys is, what is your spatial and temporal resolution of these sensors? You showed a figure showing that, the pressure ulcer takes tens of minutes to be a problem, but what is your actual spatial resolution of how big a temperature, like a spatial temperature change can you detect? And then related to that is, what sorts of things would you imagine might cause false positives or false negatives with your sensor?
For our thermistor temporal resolution, we're able to heat within seconds and we're able to cool within minutes, which is well within the range, as you mentioned. For our spatial resolution, our patch is about 6 to 8 inches wide, and we're not advertising it as being able to detect temperature around there, and our array of thermistors is evenly spaced throughout that grid. So we're able to have like a large array of sensors that can detect overlapping points within that 6 to 8 inch patch, which covers up the sacral region, as is the clinical standard for wound dressings.
So I guess what I'm asking is, how big does the pressure ulcer have to be before you'll detect it or send an alert?
Yeah, that's a great question. We compare spatially across quadrants of the patch, and so the pressure ulcer would need to be larger than just one thermistor. It would probably have to span about 5 to 7 thermistors in order for us to take those averages and be able to detect it.
And what's that size?
Each thermistor is like about a millimeter, so I would say like a diameter of, I guess, probably like 3 to 5 centimeters for our pressure ulcer. Yeah.
I thought the way that you guys described and visually showed the evolution from point of proof of concept all the way to what you are, like that was like awesome. Like it was really helpful for me to see all the progress you made and the decisions you made along the way. So I just wanted to commend you on that.
Thank you.
Cool. Great work. Thank you, Team Lavara.